So last time we did an example of a distributed load, internal loads problem, where the distributed load was uniform. So now I'm going to just say a couple general things about distributed loads, and we'll do a couple harder problems. So internal loads in the presence of distributed loads. So first, to do the calculations, remember, you always have to represent the distributed load as a point force, but don't do that until after you've chosen the body to isolate. So represent the distributed load as an equipolant point force only after you've chosen the body to isolate. So what this means is, partly what this means is, like, for example, if you're representing a weight force as a distributed load, you can't say that weight force acts at the middle and then do your cut, okay? You do your cut, and then you say the weight force acts in the middle of the cut, okay? That's a pretty common mistake for people to make. Second, the magnitude of the equipolant point force is the area of the distributed load shape. So if it's a triangular distributed load, you're just calculating the area of a triangle, that kind of thing. And then third, the x location of the equipolant point force is the x coordinate of the centroid of the distributed load shape. Okay, so let's do an example. Let's say we have a cantilever with a length of 3 meters and the mass is 50 kilograms. And we have a triangular distributed load of, let's say this goes up to 1,000 newtons per meter. And we want to calculate the internal loads. Well, if it was cantilevered on the right, we could skip the part of calculating external loads because it would never come up in the internal loads. But we can't do that here, which makes you then wonder, well, can we just walk around to the other side, and do it? But then you have the triangular load facing the wrong direction, right? And then you have to deal with trapezoids and stuff. So really the quickest way in this case is just to calculate the external loads to start with. So free body diagram of the whole thing. It's a fixed joint, so there's an unknown force vector and a couple. Let's put a torque on this too. Why not? Just to get used to having those. So let's say the torque is this direction. Let's say it's 80 Newton meters. And then that means that this fixed joint also applies an external torque. I'll call that reaction torque, TR, fancy TR. What is going on with this? Okay. And then we have a distributed load due to the weight. That is so weird. Why is it doing that? Somebody tell me.
Is it the page maybe breaks off there or something?
No, it doesn't. It doesn't do that till after. Strange. Is it worth redrawing? Maybe. What did I say that was? 80 Newton meters?
Yeah.
And the mass was 50 kilograms. Okay, so the distributed load from the weight, we have 490.5 as a weight spread out over 3 meters. So 490.5 divided by 3. This is 163.5 newtons per meter. And then we have the triangular distributed load of 1,000 newtons per meter. And then we have the couple of 80. And now that we've drawn our free body diagram, now we can represent these distributed loads as point forces. So we have the triangle with a height of 1,000 and a length of 3. And we know that the centroid is 1/3 of the length from the right angle. And so that means that this length is 3 times 2/3, so just 2 meters. And the area of that triangle is 1,000 times 3 divided by 2, so 1,500. And then for the rectangular distributed load, the centroid we know is right in the middle. And so this is just the midpoint, so 1.5 meters. Guess I did that in red before. And the height is 163.5. The length is 3. So the area is 3 times 163.5, which is 490.5. And now I can redraw the free body diagram. At the middle, we have a downward force of 490.5. Two-thirds of the way from the end, we have a downward force of 1,500. Then we have the external loads from the wall. So that's R, MR, and fancy TR. So now we can go, and we have the torque at the end of 80. So now we can go to Newton's second law. It says Rx, Ry plus 0, negative 490.5 plus 0, negative 1,500 is equal to zeros. So Rx is 0. Ry is 1990.5. And then the moment equation about the z-axis. So I'm going to, for this one, put my about point at the left. That means there's no moment from those R forces. There is the couple MR. The 490.5 has a moment arm of 1.5. And that's a clockwise moment. the force of 1500 has a moment arm of 2. And that's a clockwise moment, so that's also negative. This is all equal to 0. So MR is equal to (3735.75 Newton meters). And now the moment about the x-axis. We only have that reaction couple TR. And then the 80 going in the negative x direction. So the reaction torque at the wall is positive 80 Newton meters. Okay, so at the start, I gave you these rules for thinking about internal loads with distributed loads. And the first one I said is only represent the distributed load as an equipolant point force once you've chosen the body to isolate. Okay, so what that means is if you look at this free body diagram and you think of these as like real forces, okay, and now you go to the cuts and treat these as the locations of those forces, everything's going to be wrong, okay? Instead, what you have to do is go back to the way it really is, go back to this thing, do your cuts, and then once you've chosen the cut to isolate, then you can once again represent those as equipolant point forces. Okay, so how many cuts do we need for this body? Just one, because there are no point loads in the middle, and the distributed load functions never change. So we have one cut that's valid for x anywhere between 0 and 3. And I'm going to start by drawing the cut. So let's see. We calculated the external load, so we know now that this is 1990.5. And we know that there is a couple that way of 3735.75. And we know that there is a reaction torque this way of 80. And then there's a distributed load this way representing the weight. That's a uniform distributed load of 163.5 newtons per meter. And then we have a triangular distributed load like this. And we don't know yet what the height of that is. That's something we're going to have to deal with because I'm going to erase this in a second, but remember that we're leaving off this stuff, okay? And so we know that the height of this triangle is 1,000 over there, okay? But that's if we've gone all the way to 3, but we haven't gone all the way out to 3. We've only gone out to x, which is somewhere in between 0 and 3. And then what I'm missing are the internal loads. So we have the internal tension, the internal shear force, the internal bending moment M, and fancy T-torque. Okay, well, if we can come up with a function for the line of that hypotenuse, that'll tell us what the height of that triangle is at x. So if you think of this, let's see. So we want the function for that line. We know that the height here is 1,000. We know that this distance is 3. And we just want the equation for that line. So we know it's going to be y equals mx plus b. We know that b is 0 because at x equals 0 here, the height is 0. The slope is the rise over run. So that is a rise of 1,000 over a run of 3. And so that's 333.3 repeating times x. And so the height of this triangle is 333.3 repeating times x. Okay, now we've chosen that cut. Now we can think about turning those distributed loads into equipolant point forces. So I'll first do the triangle. This triangle has a width of x, a height of 333.3 repeating times x. We know that from the right angle, it's 1/3 of the way along the base. So that means from the other edge, it's 2/3 of the way. So this distance is 2x over 3. And the area is 333.3 repeating x times x over 2. So that's 166.6 repeating x squared. So that A is going to be our equipolant point force. The 2x over 3 tells us where it's going to act. And then I can think about the rectangle. The centroid of that is right in the middle. This is x. The height is 163.5. So this distance is x over 2. And the area is 163.5x. And now I'll redraw the cut. We have 1990.5, 80, 3735.75. Then at the middle, we have this downward force of 163.5x. Then at 2/3 of the length, we have this downward force of 166.6 repeating x squared. And then we have the internal loads T, V, M, and fancy T. Any questions about that? Okay, so now Newton's second law says 0, 1990.5 plus 0, negative 163.5x plus 0, negative 166.6 repeating x squared plus t negative v is equal to zeros. And so t is equal to 0 and v is equal to negative 166.6 repeating x squared minus 163.5x plus 1990.5. What about the signs of those vector components? Does that make sense to everybody? Remember that you're drawing this with, like, think of this as a number multiplied to a unit vector, okay? So you're always, like in this case, you're multiplying 163.5x times a unit vector in the negative y direction, 0, negative 1, okay? And so that's why you get this negative component there. Same thing with the, well, it was here. Same thing with the x squared term. Now this is the time-consuming one, rotational Newton's second law about the z-axis. My about point is going to be over here. Okay, so I know I'm going to add on that couple at the wall, so 3735.75. The 1990 doesn't produce a moment. We have a clockwise moment with a moment arm of x over 2 and a force of 163.5x. Clockwise means negative. And then we have another clockwise moment with a moment arm of 2x over 3. Times 166.6 repeating x squared. And then plus m minus vx is equal to 0. So m is equal to, we have positive 111.1 repeating x cubed plus 81.75 x squared minus 3735.75 plus v times x, and then the v is this thing in the box, so we have minus 166.6 repeating x cubed minus 163.5 x squared plus 1990.5 x. And now we have some terms we can group. These two, these two, and that's it. So m is equal to negative 555.5 repeating x cubed minus 81.75 x squared plus 1990.5 x minus 3735.75. Any questions about that one? And then the easy moment equation, Rn2L in the x direction. All we have here are a positive 80 and a positive fancy t. And so that tells us that the internal torque the whole way is just negative 80.
The torque arrow on the force is going to the left, so right?
The force, which one?
The 80.
It's going to the, it was going to the left on the right side, but then we calculated it over here, and it has to be equal and opposite, so it was going to the right then.
Sure.
Yeah. Any other questions?
Pin joints can apply that torque as a reaction
Yeah.
force, right? Okay.
Mm-hmm. Okay, what was I going to say? Oh, so now let's do the derivative checks. So the derivative checks say dm dx is always equal to v. And negative dv dx is always equal to q. Okay, so now we have this time we have a function q. So what does that function q mean? Well, let's do the first check first. So dm dx, let's make sure that that equals v. So dm dx, we have negative, oh, this shouldn't have been 555. This should have been just 55. Sorry about that. Okay, so derivative of this is negative 166.6 repeating x squared, so that term works. Derivative of the x squared term is negative 163.5 x, so that term works. Derivative of this one is 1990.5, so that one works. This one has no derivative, so dm dx is equal to v, so that works out fine. Okay, now the question is, what about negative dv dx? In order to check this one, you have to calculate what the distributed load function is. Okay, so what's the distributed load function, the downward distributed load function here? The downward distributed load function is the function of that line of the triangle plus the function of the line of the rectangle. Okay, so that is going to be 333.3 repeating x plus 163.5. Any questions about that? Okay. So let's take these derivatives. You get, so negative dv dx for this first term is negative 333.3 repeating x. That one matches. And the derivative of this with respect to x is 163.5. So that one matches. And then 0. Any questions about that? Okay, I don't think I'm giving you in this class anything other than triangular. I mean, you don't have to worry about parabolas or anything. So this is enough. There is one thing that I want to point out. I sort of mentioned this earlier, but what about a problem like this? It looks pretty similar to the one we just did. Okay. But the problem here is when you do your cuts, so the triangle facing this direction is a pain. Because when you do your cut, it won't be a smaller triangle anymore. It'll be a trapezoid. You know, because that's the piece that we're cutting off. Okay. Well, it's definitely not impossible. I mean, you could do it like this. Break it up into, so this trapezoid has a height of 1,000 over here. Over here, it has a height of mx plus b, where you just have to come up with the equation for that line. Okay. That means the height of this So this is the whole thing is 1,000. That means the height of this triangle is, mx plus b minus 1,000. So it's not impossible. Hold on a second. But it does take longer. A better way to approach this is just walk to the other side of the beam before you do this problem. Then this problem is like this. And that's just easier to do, faster to do. Any questions about that? Okay, that's it for today. I'll give you some more stuff like this. And now we'll get started calculating internal no, these are the internal loads. We're going to get started calculating the stresses that come from these internal loads.